This time, let's talk about how we can linearize the nonlinear equations of motion. Well, suppose that the inverted pendulum equations of motions are having written as theta double dot minus sine theta. So here sine theta is a nonlinear term. So what we have learned in undergrad courses are we can assume small angles. So sine theta is going to be approximated as a theta. But however, that's the case, the very special case when theta is a small angle with respect to the zero. But maybe sometimes, especially for the biomechanics, when we analyze a human motion, you'd like to linearize the motion with a specific posture, like a bending posture or certain like a non-zero posture. So that's what we are going to talk about in this section. Okay, to work on those linearization, let's review Taylor series expansion. So Taylor series expansion with respect to the x naught with the small value delta xx is going to be expressed by its function value f of x naught and its first derivative and the magnitude of the delta x, and second derivative and the delta x square, and nth derivative and delta x to the n. And also there are constant the factorial number in front of it. So based on those Taylor series expansion, if I expand the sine theta, it's going to be sine theta naught plus something delta theta and something delta theta square, delta theta to the cube, and quadruple. So for very, very small delta theta, those higher order term is going to be a lot smaller than this first order term. So you can approximate sine theta naught plus delta theta is going to be approximated as sine theta naught plus cosine theta naught and delta theta. And for very special case, when you're doing the linearization with respect to the theta not equals to zero, like upright posture, then you can formulate this as a sine delta theta is going to be delta theta, which is accordance with this small angle approximation. Okay, so now let's linearize human posture with this leaning forward posture. So suppose that you have a theta naught with maybe 10 degrees leaning forward, and how we can linearize them. So to maintain a forward motion, we know that there should be some torque offset applied for the ankle, right, to maintain that posture. So there are actually 4 steps to linearize these equations of motion. The very first step is you should find the equilibrium, the reference point. So here, maybe leaning posture. So at equilibrium, the old external forces are balanced, so you don't have any acceleration term from F equals ma. So from your original equations of motion, those theta double dot term goes to be 0. So here you can get, my equilibrium torque applied at the ankle to maintain that theta naught forward leaning should be this much. Okay. Now, let's plug in theta in terms of theta naught plus some deviation. So from your original equations of motion, I will have theta naught double dot plus delta theta double dot, and sine theta naught plus delta theta, and torque naught plus delta tau. And since I have assigned this nonlinear term, I'm going to do a Taylor series expansion for that. So I'm going to have sine theta naught plus cosine theta and delta theta multiplication. I linearize them, the kind of approximation. Okay. Now, since I have those equilibrium condition here, if I plug that in to here, I can say, this torque tau naught is going to be expressed by the theta naught. So those been canceled out. So what I can have finally is going to be only the linearized formulations of delta theta here and delta tau. So if I assuming theta and tau is defined with respect to the equilibrium, I can just rewrite the equations in terms of I naught theta double dot minus mg sine theta with a newly introduced parameter cosine theta naught here, and theta and tau. So this is a linearized form with respect to theta naught. And note that here theta and taus are defined from small deviation with respect to the equilibrium point. So we can actually apply this when we actually analyze a real human data. So as I said, your posture is never like perfectly zero with respect to the mostly the reference point, like earth horizontal or vertical. So even your upright posture might have a little bit of a initial leaning. So you should linearize your posture with respect to that point. And suppose that you want to analyze some motion of the sports, and then this player maintains their bending posture, right? So if you want to analyze what's gonna be the load at the lower back, joint torques, etc., you should linearize the with respect equations of motion with respect to bending posture, and it's gonna be a really good fun topic that you can work on by yourself, maybe at the homework.